Okay, hello everybody and good morning. So we're ready to begin the second day of our workshop, and we're very happy to open with Alejandra Castro from the University of Amsterdam, who will be telling us about the holographic landscape of symmetric product orbifolds. As usual, feel free to chime in with questions during the talk, unmute yourself. All right, Alejandra, over to you.
Thank you, Suresh. So I wanted to thank the organizers for hosting this meeting. So it's good to, well, I'm not really seeing many people right now, but well, it's good that you're all here connected virtually, and that we can have this discussion on my favorite subject, black holes and BPS and BMS and integrability. So I'm very excited that this workshop is happening. And today, I want to tell you a little corner of what we have been exploring in this context. Black holes are not going to be, I will mention them, but unfortunately, only for my taste, they're not going to be the most prominent character in this talk. But it's still, yeah, lots of quantum gravity at least. So without further ado, because I tend to not be able to finish this talk in time, and I do want to finish it on time, let me just give you a bit of references on who this is based on, because I really want to highlight my collaborators. So this started back in 2016 with Alex Bellin, Joao Gomez, and Christoph Keller. But most of the talk, so this is kind of like our first encounter with the subject, and we were trying to understand the structures that were showing up. But most of this talk is going to be based on these last 3 papers, which also include my PhD student, Beatrix. She's applying for postdocs this year. And also this last paper that involves Nathan Benjamin and Sarah Harrison. So these are basically the 3 main references that we'll be using. So, okay, so what is the point of the talk? Because the title sounds kind of complicated and convoluted, but it's my effort of trying to be precise on what we're doing. So, but what is the theme? So what are we trying to do with these papers? So, as we all know, ADS-CFT gives us some definition, a non-perturbative and UV complete definition of quantum gravity. And we are all super familiar with the fact that there's some conditions. We talk about conditions on CFT such that you get like a semi-classical gravitational feature. So I'll be more specific on as we go along on what are these features. But in general, like this whole jargon that we're familiar to, like, oh, there's some large N, a factorization, and there's like some conditions and locality and the bulk, and I don't know, there's all this like kind of intuition that we have about like what does it mean for a CFT to have this semi-classical description. And so a natural question as we're trying to understand what ADS-CFT is as a fundamental mechanism behind quantum gravity is that you could then very fairly ask, okay, that's great. We have this framework. How will you go about building these conformal field theories? So we are all in this audience at least true believers of the correspondence. And so if you take a field theory perspective on this question, you should be able to quantify and characterize the classes of conformal field theories and build them in some constructive way such that you can claim that they have this semi-classical feature. And this is part of like the question that we were interested in addressing. Now, I'm not going to do it in any number of dimensions. This is, of course, as all of you are aware, it's not an easy question. We'll have to make compromises. I'll start putting myself in a corner as we go along, and that's why the title is a bit more technical. But what I want to kind of illustrate in this talk that although I'll be talking about this in the context of ADS-3-CFT2, and there's various properties of ADS-3-CFT2 that are not universal. They're going to be very specific to the number of dimensions that I'm working on. But I think it does illustrate the challenges, and it illustrates the fact that we can make progress in addressing these type of tasks in our field. So with that said, the talk is going to be basically divided into 3 parts. And there's going to be 3 different subjects that I'll touch upon. So to build into how are we trying to address this question. And each of these 3 directions that we're going to explore have their own kind of keyword attached to them. So we'll first discuss holographic CFTs. And so by universality, I mean, so as we explore this door, we're basically going to consider what are necessary conditions on the spectrum of this CFT. So when we talk about the semi-classical description, what are things that we want, like basic things, okay? And what you should be like paying a lot to attention here is the fact that, yes, I will impose some conditions that we consider like minimal. At the least, we should be able to satisfy, to meet those conditions. Sorry, I'm going to. We should be able to satisfy those conditions, but the name of the game here is what is a set of sufficient conditions, okay? So when do you decide that you impose all the conditions that you needed on the CFT and then everything else will come for free? So this is what I find very, very interesting about this thing, the contrast between necessary and sufficient conditions. Then on the second part of the talk, I'll start making some compromises because, as you know, the space of conformal field theories and the space of conformal field theories in 2 dimensions, it's not as understood as we perhaps wished. So I'll restrict to the subject of symmetric product orbifolds, and even further, I'm going to restrict to basically supersymmetric quantities in this classes of theories, okay? Because that's what the technology I know how to use, and it will still give us some rich arena, like we'll still have lots to explore, but I'll be narrowing the questions by then. And at that point, after we kind of like, so here's where I'm setting up what the strategy is. Then the third part of the talk will be basically the output. So we're going to have the set of necessary conditions. I'm going to specify where am I going to explore these conditions. And then, yeah, so did we manage to find CFTs that meet this set of conditions? And the answer will be yes. It's going to feel, well, I hope I give you the feeling that it feels like looking for needles in a haystack. But we did find needles, many of them. There's going to be an infinite family of conformal field theories. And the main player there and what allowed us to basically identify these theories was the minimal model classification in 2 dimensions, as I'll specify more. But we basically have, nowadays, we kind of have a lot of information, so we can start even scrutinizing more carefully this issue of necessary versus sufficient. So, okay, so that's the plan. That's how we're going to proceed. So let's get started with our first task, describing holographic CFTs. And as Suresh said, if there's a question, anything, I'm going to start saying perhaps things more controversial from now on. Please interrupt me, okay? So very good. So let's talk a bit about ADS3 gravity. Okay, so what do I have in mind when I say semi-classical description of gravity? So what I have in mind is that from the gravitational point of view, when 1/g Newton is very big, I want to have a theory of gravity that one piece of this theory of gravity is going to be basically the Einstein-Hilbert term, okay? And it's going to be the Einstein-Hilbert term coupled to some matter. And here, as matter, as good string theories as we are, you can think of like basically, so you can have in mind that you will have some set of scalars, of gauge fields, of fermions. And even as more as a string theorist that one is, like you can also think of them as this being some supergravity description, completion of it. But basically you can think that this is at low energies and the gravity side, like I have basically my plain vanilla like type of theory. I'm not considering higher spin theories in this context. I want the highest spin allowed to be spin 2. So nothing crazy. This is my expectation of the gravitational description. And in this context, so for this classes of theories, I'm going to, there's a lot of aspects known, and there's a lot of universal properties in this context. And so what will be important for this talk is that there's going to be, as we consider the spectrum, so we'll be imposing conditions based on this type of theories. We'll be imposing conditions on the spectrum. And what's going to be important is that there's light states in the spectrum. So there's perturbative states coming from the wiggles of these massless fields. There's also going to be the Brown-Hinault states, the boundary gravitons coming from this side. But that basically is what I'm going to consider generic. Like we will always expect to have some amount of perturbative states. There's also going to be heavy states. So this is the BTC black hole. And this is always guaranteed just based on the fact that I have this term. And in general, there can be other stuff. So I'm not going to be, this is what I will consider kind of non-universal. They're going to be present. They will be important if you want to make more refined statements about the correspondence and how the dictionary works, but I'm not going to focus on this. So this will depend a bit on the details of like what the theory is and so forth. But so this you can leave, this third point is like later task. But okay, the other thing that is universal in this entry is that in our ADS3 CFT2 dictionary, we equate the central charge to the ADS radius in Planck units. And the basic part of our lore is that we're looking at this correspondence when the central charge is very big, okay? So that's the number one. If you wish, you can phrase this as the number one condition on the CFTs. I'm going to be like trying to understand and quantify two-dimensional conformal field theories at large C, okay? Very good. But let's refine a bit more these conditions. So besides asking for large central charge, there will be two more conditions that I want to discuss. One portrays the black hole. So this is where I'm going to be talking a bit about black holes and then kind of forget about them, because then there's actually going to be a more stringent condition, a stronger condition on the perturbative part of the spectrum. Okay, so this will impose, this will be harder to meet relative to this requirement here, at least the way that I'm phrasing it today. So, but let's talk about the black hole regime, because I was super happy that Samir mentioned. Yes.
Can I ask a question?
Yes.
So in particular, should there be a mass gap? I mean, should there between sort of the light graviton-like states and the black hole? Are you saying there's a parametric mass gap? In principle, yes, there should be a mass gap so that the higher spin states are basically parametrically like separated by the other ones. But so
I'm not
only,
going to,
the question
I'm
was,
not
is
going
there,
to
sorry.
pose it today explicitly. So this is, I'll talk about it as we go along, as we discuss more this perturbative regime. I'll explain how we impose bounds there, but it's not exactly the mass gap. Although I would love to impose that as a condition. It's just that it's a little bit hand wavy as a condition at this stage.
I see, but what I'm asking is there another scale in the problem or only the black hole scale? Is there some other?
No, we'll have like we'll have the string scale and the ADS scale.
But there's a string scale which is different from the Planck. Okay.
Yeah. I have a. We'll go through that as we go into this stuff, because there's basically, from my point of view, there will be three scales: the Planck scale, the string scale, and the ADS scale.
All right, thank you.
Okay. So black holes. So we know black holes carry entropy. We like them when their sizes are large in Planck units. And if you go through the dictionary here, it basically tells you so here you're just using the basic entries. So this is just a dictionary of ADS-CFT. So the statement that the black hole is large in Planck units is basically a statement that the energies of the states that you're looking at can be comparable to the central charge, and these two numbers are bigger than 1. Now, as you try to account for the black hole entropy as a number, as some microscopic number of states in the CFT, there's two things that go in here. So for instance, from going from this step to this other step, this is what you can do kind of quickly, basically following what Samir it's basically the same thing that Samir was discussing yesterday. There's basically a modular transformation that allows you to estimate the asymptotic growth. And this is usually what we call the Cardy formula. And then from this type to this type, again, you're just using the ADS-CFT dictionary, okay? And so this is the famous Strominger-Vafa result that then Strominger generalized basically for any theory of 3D gravity that contained the BTC. And yes.
Just to nitpick a little bit, I mean, these transformations need E to be much larger than C, right? As you know very well.
Yeah, I'm about to get there.
Ah, okay, all right, sorry.
So I'm just, yes. I know exactly because we wrote a paper about this as well. So yeah, I'll come to that in a second. But I just want to say, like, usually how this was like sort of and historically how these things were realized was that, oh, you write down what the Cardy formula is, which gives you the asymptotic growth here, and then you use ADS-CFT, and then voila, you get it. It's beautiful. It's an exciting, very important match. But as Samir was, because he knows this very well, you have to be careful because actually from this step to this step, this actually tells you that E has to be very big, but C is fixed. So this is basically what goes behind this Cardy formula. And it's basically the same that Samir was mentioning in the cases of ADS5, CST4. So you could look, so he was phrasing it as a statement that you could do like fix N and then take states with very large energies, but there's an order of limits that it's very careful. And this statement is very different from this statement, okay? So there's an overlap, of course, and that's why things then work out so beautifully. But if you really want to describe, want to claim that the CFT captures the entropy of the black hole, you need to be able to argue that you can do these manipulations from here to here in this type of regime, okay? And this is a non-trivial condition on the conformal field theory, and this is what usually people call the requirement. So at least in the 2D jargon, sometimes we call it like just an extended Cardy regime. So the validity of this step actually, you can argue that it goes up here, okay? So this, you can view it as a condition on your conformal field theory. And people did, so you can, of course, impose that as a condition, and it actually restricts the perturbative part of the spectrum. So if you demand that you have this extended Cardy regime, when energies are of the order of the central charge, the perturbative part of the spectrum is not allowed to be whatever it wants. And there's, for instance, these two papers that quantify this to some extent. And so there's this, for instance, in this paper over here, it was phrased as the requirement that you had a Hawking-Page transition. That's basically the same as phrasing, as saying that you have this extended Cardy regime for the purpose of this talk. And in the BPS context, so looking, which will be what we will be following more we go along, there was also quantification of how the BPS spectrum had restrictions. The perturbative part of the BPS spectrum got restrictions because of this requirement of having an extended cardio regime. Okay, so the black hole already influences this. So that's why from now on, I'm going to be talking, I want to digest a bit more this perturbative part of the spectrum, okay? Because I know that if I have this under control, then parts of the black hole description will come for free. Okay, so let's talk about that. And as Samir was asking me, okay, so let's discuss a little bit my biases, because this will basically help me telling you like from which angle we're coming from, what are our assumptions, and perhaps limitations of what we're doing. So this is based on how basically my experience at trying to understand ADS3CFT2 and understanding it from a string perspective. So we basically have 3 scales in hand. So we have the Planck scale, the string scale, the ADS scale. I'll be a bit, this is going to be extremely hand wavy, but let's sort of understand what do we encounter as we're studying this perturbative part of the spectrum, okay? So I'm only going to be, this Planck length is always going to be way up here, and I'm going to be considering that then I have these 2 other hierarchies here. So there are situations, at least, and it will be relevant to the ones that we're encounter, where basically the ADS scale is very close to the string scale. This is what I'm going to be kind of colloquially calling, like quote unquote, some like weakly coupled description. Okay, it will be a bit more, regime. Okay, so when the string scale is parametrically comparable to the ADS scale, so I have these floppy strings, usually what happens, well, my experience is that what happens to the number of states that have energies that are measured, so or they have conformal dimensions that I'm writing as energies measured in ADS units, for states that are very energetic from this point of view, but they're not reaching the Planck scale, so they're still quite below there, so they're not black holes. So this is what I will be calling like perturbative states. What you might tolerate in terms of like how many states can we tolerate before anything becomes too problematic, is basically what we'll be calling a Hagen-Dorn type growth of states. Okay, so this is pretty characteristic of many string cases, and it's and we'll see it as we go along. The thing that is interesting about the reason why I'm also highlighting that this is something that can occur to you, and we'll see it in the CFTs, is that this is enough to meet the black hole regime condition. So if you have a CFT for which there are operators that basically scale, that are big but are not scaling with a central charge. So this statement here is basically a statement that H is very big, but H also is just scaling, is not scaling with C. This is enough to meet the black hole condition. So basically, this D of, if the perturbative states are of this form of Hagen-Dorn, and where this number, so if this is basically bounded by 2 pi h, then you're going to find that the black hole entropy will match the Cardy entropy in its full, in this extended Cardy regime. So this is one of the things that this paper by Hartman, Keller, and Stoika showed. So even if you have Hagen-Dorn growth, you'll be able to have this Hawking-Page transition. So that's why this condition is not super stringent, because I don't want to describe a string spectrum today. What I have in mind is that I don't want these 2 scales to be similar to each other. I want to make them parametrically different. So what I want is to have a separations between the scales, that the string scale is much bigger than the ADS scale. And from that point of view, I'm demanding that the same states that are going to be very energetic, but not scaling with the central charge, have a slower growth. So they're going like an exponential to h to the gamma, but this parameter gamma is strictly less than 1. So if gamma is equal to 1, I would have said, this is Hagedorn, but I want gamma to be much less than 1. And in particular, for instance, it's good to write a little example here. So if you have in mind that you have some compactification that is like ADS3 times some manifold that has basically both of these manifolds have an ADS, like they're basically of the size, this lambda ADS. So it's like you can think of like ADS3 times S3 or something along those fashion. This what you would expect from this parameter gamma, you would say, okay, if I have some bulk or some gravitational effective field theory description of this theory, this gamma just from dimensional analysis should be d minus 1 divided by d. And this number is always less than 1. And this is just basically the statement that the free energy of this gas of particles that you can fit inside of this box that is ADS times m basically will scale like the temperature to the number of dimensions. And this number here is not scaling with G Newton. Okay, so it's independent of G Newton. So you just have basically a box filled with particles floating around. And so from the point of view of what I expect from a gravitational spectrum, from a gravitational spectrum, is that I want something that is slower than Hagedorn. So that's why I'll use this terminology of slow, because I want the power here to not exceed that, and that meets this criteria. Now, as Samir was saying, so this is what we will call, also this condition goes under the name of a very sparse condition on the spectrum. And it is interesting to contrast it to what the other condition on the spectrum that you could have thought to impose, which was the gap in the spectrum, the fact that you don't want conserved currents that have spin bigger than 2. I have been curious to try to see if one can show that one implies the other, or how they're different. I don't think there's a sharp statement on how this condition of sparseness, so as we write that this is what we expect from the growth of states, matches the delta gap. But I'm not going to be, so what we will be doing is imposing this condition, but I do think it's terribly interesting to understand if that tells us something about some guaranteed on having this gap. I'm hoping it will, but I don't have a proof, unfortunately.
Yeah. Can I ask a technical question?
Yeah.
This condition that you're going to be imposing,
yeah,
what does it really mean mathematically? I mean, is this an asymptotic statement, or is it supposed to be?
It's an asymptotic statement.
But that's confusing, because you're saying that E is not going all the way to infinity. So what?
No, so I'll first, so what we do, and from the point of view of the functions that we're manipulating, we first take C to infinity, keeping H fixed.
And it's an asymptotic in that as C goes to infinity for fixed H, is that the statement?
So this will be, so I'm thinking here that in some way C is already very big. And so the first thing we do, so I'll show you the equations, but in terms of like building this generating functions, we first take the strict n going to infinity limit without touching the conformal dimensions. And so that basically,
but what does that mean on a computer? Is it that some ratio of the central charge to H is fixed as you scale both, or what are you actually doing?
You have to remove pole, but it's basically we can talk. It's just that right now I haven't introduced enough equations. But,
okay, yeah. This is also a technical question. We can speak about it.
It's a technical question, and it's explained like Jan de Boer did this when he was comparing the spectrum of ADS3 times S3 to the K3 sigma model. So it's basically the steps. And so you take n going to infinity while keeping the conformal dimensions fixed. The resulting object basically measures any state that has h up to, h can be very big, but it will never scale with the central charge. So it basically removes any black hole from the counting formula. And you just get what you would have called like the perturbative part of the, in his case, the BPS spectrum. And that's what he matched, like when he was matching the supergravity spectrum, that's what he matched against the spectrum of K3.
Yeah, I had the same question about his old paper, but let's discuss this later. Yeah.
Okay, but yeah, and the resulting object, then it's like we can build like a mini partition function for that object and extract the asymptotics out of that. So that's basically what we're doing. But yeah, okay. So because I go so slowly on this, sorry. So okay, the size is 9. Set up. So basically with these conditions, I just want to summarize. So what's happening is that, so we discussed basically we discussed the fact that we wanted the central charge to be large. We discussed what are conditions that the black holes will impose and basically what are expectations that you will have from the perturbative part of the growth. And conformal field theories that meet these requirements, so that basically obey this, although I shouldn't, like, as I was pointing out, 2 is stronger, like 2 kind of encapsulates 1. So I should just put them in as just one condition because this one is stronger. But basically, a CFT that meets these conditions is what I'm going to be referring to as holographic CFTs. And the name of the game is like, how do I know what are holographic CFTs versus CFTs that are not? Okay, very good. So let's try to understand how to then answer, like quantify that green region there. So let's start talking about symmetric product and algorithms. So all the conditions I've phrased so far basically are imposing conditions on the spectrum of the conformal field theory. So as I try to quantify the space of conformal field theories, there's 2 things that I want. I basically want CFTs with large central charge, and I want to have control on the spectrum so that I can actually see how these conditions are met. And so there's in order to get theories with large central charge, there's an easy way how to do that. And it's basically this construction of symmetric product theories. So what you do is that you grab one theory, which so you grab one theory that I'll be calling the seed theory. So you grab one theory C, and then you tensor it m times, and take and quotient by the symmetric group. And so what happens is that if this theory had central charge C, then the resulting object has central charge m times C. And so if I take m to infinity, then it makes the total central charge go to infinity. Okay, so it's a pretty easy and way of like meeting my first requirement. Okay, so you grab one theory, you grab your favorite theory, and then you do the symmetric product, and then you'll get a large central charge theory. Okay, and the seed is basically your representative in this construction. Now, the other reason why this is super nice as a construction is that you have a lot of control. So based on the fact that you know what the seed is, then you have control on the spectrum of what the symmetric product is. And so this is encapsulated by this formula, the Dijk-Moore-Verlinde formula, which basically what they showed was that it's convenient to not talk about the partition function for each value of m, but actually build like what they would have called a second quantization, or third, whatever, okay, an extra quantization of the system, where you add another fugacity that we'll be calling P, and you're basically averaging over the theories there, M, okay? And so the thing that is nice about looking at this object is that these guys individually are horrible. They're like some Hecke transforms on the seed. It's super disgusting. Like it's really, really difficult to stare at. My eyes still hurt when I just look at one instance. But if you look at the collective, then you get this beautiful product formula. And this formula is super nice to write. And so that's why I'll keep on writing it. And then here, all the information that you need is to know what are the degeneracies. So this input here, so this guy would have basically degeneracies that you would have called d sub n. And so if you know the d sub n's, then you evaluate them at d of m times n, and then that's all that you need to know. So if you know these guys, then you know everything that you need to know about the spectrum. And this product formula is illustrating that fact. So that's great. We have tons of control on the spectrum. So it looks like I'm good to go. Unfortunately, I'm an idiot. So, the problem with this beautiful construction that gives me tons of control is that one of my collaborators showed that any symmetric product, if you look at the partition function of any symmetric product, no matter which symmetric product you look at, so all symmetric product theories basically have, if you look at this growth of states, they basically all have this Hagendorn fast growth when the conformal dimensions of the operators are much bigger than 1, but H is not growing with the central charge. So they all kind of look like string theories. So any symmetric product theory, which is kind of like obvious from the picture. So in this picture here, like this is what I would have called the weakly coupled description, because I tensor the theories and I kind of gauge them a little bit by like, this is basically like the analogous of gauging the theory in this context, but the copies are not really interacting. So it's kind of like, they don't care too much, modulo the fact that you're imposing some boundary conditions and getting twisted and untwisted sectors. This is like what you would have called a weakly coupled description, and then you get this Hagendorn-like spectrum. And so it's kind of not my semi-classical theory of gravity that I was really aiming for. It feels like, yeah, Alejandra, you're studying the empty set. Good for you. But okay, but we'll be a little bit more resourceful than that, because we know that these theories do appear in our favorite systems. They appear in D1, D5. So let's think a little bit outside of the box. And so okay, so the way that we're going to be thinking about this problem is the following. So I want you to think that we have some moduli space of theories. Okay. By moduli space, I mean that I will have some set of marginal deformations and that describes a set of theories that are continuously related. And so what I have in mind in this picture is that the symmetric product description is like one point in that moduli space. By then, if I then add a marginal operator, which will have a coupling attached to it. So there will be a strength to when I add that as a deformation of the theory. It will drive the theory to some strongly coupled point, and that's where I have my gravity description. So this is a point where lambda string is basically, so the symmetric product description is when lambda string is similar to lambda ADS, and I have the stringy part, and then this is where lambda string is much bigger than lambda ADS. Okay. And basically this coupling here is what is putting the separation between the string scale and the ADS scale. This is what is inducing this like separation of like what's lifting the fact that I added this coupling by this marginal deformation, kind of it's what's lifting this two, making these two scales different. Okay, and this is how we think things work out in the case of, for instance, D1, D5. This is the way we think about this instance of ADS3 CFT2. And so what in my pursuit of trying to understand some subspace of the space of theories, then I could say, okay, I can still consider this symmetric product description, but then what I should have in mind is that in order for them to have some holographic property, I should think of them as like as something for which I add a marginal deformation, and then this makes the theory become like gravity-like, okay, holographic. Okay, so this marginal deformation is what's going to remove this Hagendorn growth and make this spectrum sparse. Now, in general, so this is also where we're not super good at fully understanding what the marginal deformation would do for finite values of lambda. So this is not an easy thing to do. So I'm not going to do conformal perturbation theory today, although I will do it it's in my to-do list in my bucket. But what we usually do is that, okay, provided that this guy exists, what then one does is focus on quantities that are protected. Okay, so quantities that don't depend on this coupling lambda. And those quantities that are protected should already meet gravitational features. And so this is where we kind of like end up in studying the BPS spectrum, because the BPS spectrum doesn't depend on which point on this moduli space you are on. And so if the BPS spectrum is already Hagendorn, it's going to be Hagendorn everywhere. So there's no matter how many marginal deformations you add, it's still going to be Hagendorn. But if the BPS spectrum is sparse, it already indicates to you that there might be modifications in the whole like spectrum itself, because the BPS spectrum basically, just to emphasize, it won't depend if I compute it at this point or if I compute it at that point, because it doesn't depend on, as an index, it won't depend on that coupling. And so if I compute it here, it should indicate something about what I expect the theory to behave at that strongly coupled point. And that's usually what we do in the context, for instance, in the context of D1, D5. So.
Sorry, may I ask a question there? So just to understand the notation, so the D1, D5 system, is it in your notation Hagendorn or sparse growth?
The symmetric product point is Hagendorn.
Is Hagendorn, and the supergravity point is
It's
sparse
very
growth?
sparse, yeah.
But the BPS states are the same. Yeah.
Sorry. Oh,
but
go
the
ahead.
BPS spectrum is the same.
Yeah, the thing is that, okay, so there's the D1, D5, its partition function, because D1 defined at the symmetric product point has higher spin currents. And so its whole partition function is Hagendorn. It's just, but then here we expect that after you add this marginal deformation, then the partition function of gravity won't have any of this. Well, if you make the separation with a string scale, then the low energy description here doesn't have all these like stringy states. They all kind of get lifted. But the D1, D5, the BPS part of D1, D5 doesn't have Hagendorn growth. And we'll see that as an example.
And then the thing you said in the previous slide, somehow that relies on it being non-BPS. I thought that's
yeah, this basically relies on the fact that all the coefficients are positive. So if all the coefficients are positive, and that's why it relies on the partition function. So this is a statement that if you just grab the partition function of any of these theories and you assume positivity of these coefficients, then the positivity of these coefficients just tell you that it's going to be Hagendorn as you do the symmetric product orbifold. That's the only thing that Christoph assumed.
All right,
the coefficient, there were no cancellations among the coefficients. Which is, and so that's why like the partition function, not the index, but the partition function is always going to have Hagendorn at the symmetric product point. It doesn't depend on the seed. But okay, so that's why we will look at quantities, that are protected, and then try to get an idea of what's going on. So from this point of view then, so as we try to understand the space of theories, so I'm already making a compromise here. So I'm not going to, well, we don't know what the space of conformal field theories is. So we're just carving out a space of conformal field theories that are built on the symmetric product. They're going to be super conformal field theories. And the question is, is there an overlap here? What class of symmetric product theories, if I look at their protected quantities, will meet this criteria? And here I added a third criteria, which is basically I need to, for this theory, to have a marginal deformation, because otherwise, yeah, it would also be kind of weird to be, yeah, talking about them in this, in the way that I'm setting up the problem. So the marginal deformation will also be now part of our requirement based on the fact that I'm deciding to study this class of theories. So just to be a bit more specific on the type of protected quantities that I'll look at. So basically we're looking at the elliptic genera. So this, Samir was discussing this yesterday, is basically the same object in 2 dimensions. This is a weak Jacobi form of index T, which we'll be using very heavily. So this was key in order to understand the properties of the spectrum. And we'll take basically the symmetric product orbifolds of this elliptic genera. So it will look something like this as we take these, sorry. So now, because I'm so annoying, this M that I wrote before is basically like T times R. It's just convenient to grade it by T. That's part of the construction. But basically now we will be looking at that object there. And the condition, so just as a minor note, this is defined in the Ramon sector, but our condition of light states, so the perturbative states live in the NS sector because that's where you have the ground state. And so basically what we'll be imposing, and here by infinity, I mean that, so C, which in this notation is basically, so now let me put squiggles because I'll be more precise as I go along, but it's basically C times R is taking to infinity, okay? And so this will be our condition on the spectrum. So we'll basically look at elliptic genera that are the way that we're going to go through them is based on their relationship to Jacobi forms, and we're going to be imposing this condition on their spectrum. And again, just to emphasize, if we looked at just the partition function, you would have gotten that gamma was equal to 1. But the elliptic genus, the beauty of this -1 to the f is that it can display cancellations. And these cancellations, that's why there's a hope of them to be sub-Hagendorn. They don't have to, they could still be quite big numbers, although you have a -1 to the f, but this is what gives us some hope. And it also makes it a quantity that is protected. So they can capture basically something about the theory in this strongly coupled point. And the spoiler, because now I have like 10 minutes left, a bit too slow, is that we will be able to tell you basically which weak Jacobi forms meet this criteria. So which of them will satisfy this condition. And new examples that at least I haven't encountered of holography will show up as we're quantifying this, okay? So that's the bottom line. Very good. So this is what we have. Okay, now let's go and see. So that's my strategy. Let's go and quantify the space of symmetric product orbifolds for which their supersymmetric spectrum meet the criteria. Okay, so there's quite a lot of procedure that goes into doing this, but I'm not going to, unfortunately for some years, like disappointment, but I'm happy to talk to you about this offline. Yeah, I just wrote down what the final answer is for the spectrum at infinite n, but to give you a little bit of a teaser, so just what we do is that we select a Jacobi form, so which we write as something of weight 0 and index t, and the maximal polarity is a number that we call b, and this Jacobi form. So this is what basically for us, the space of Jacobi forms basically distinguishes for us like the space of theories or the space of elliptic genera that are non-trivial. Then, okay, so you grab a weak Jacobi form, then you do the symmetric product orbifold of that. It was useful for some of our purposes and understand why this was the perturbative part of the spectrum. So this is papers, this is the second paper that I listed, was basically where we showed why this quantity was the perturbative part of the spectrum. But to do that, we basically relate this to what we were calling a Siegel paramodular form. And so it gave us the control of defining this function and extracting it out of the symmetric product. And then what we're imposing conditions. So what we wanted to be very sparse are these coefficients, which are basically dictated by this. And I'm not telling you this object here, this f of HL, it's something that, again, it's some sum of coefficients of the seed, but given the constraints on time, it's not going to, yeah, we can talk offline about what this is, but this is basically just something that is dictated by the seed itself in the same way, in a similar fashion as the DMVB formula. But now, what is the punchline? So the punchline is that we proved that there's only two things. So if you hand me a Jacobi form, I would go and call Beatrix, my student, and be like, Beatrix, tell me if it's fast or slow. And so basically we proved that there's only two things that can happen. So you give me a Jacobi form, you build this object out of it, and there's only going to be two types of behaviors. You're either going to get like some of these stringy examples. So this will be in the category of what I was calling fast, the Hagedorn-like growth. So here you get like this linear power in H. In the powers up here. So this is basically a statement that there's not cancellations, and then you get this linear growth. Or you can get a slower growth. So there will be also cases where these powers here just all collapse into Kronecker deltas, schematically speaking, and then the growth is much slower. So it's square root of H, which is basically in the notation that I was using before. It's this gamma equal to a half. Okay, and so this is basically slow. But the thing that is kind of interesting is that it's either linear or square root. There's no other powers that appear. So here I'm not being like, oh, it kind of, and you can get things in between. No, you give me a Jacobi form, it's either going to go linear. The number here might be different. It can't exceed 2 pi, but it's basically something that will tell you exactly when you set the ADS scale equal to the string scale, it will be like, oh, they're equal with a factor of like a third or something, like something along those lines. But in terms of powers, you either get the 1/2 or linear. And that's it. And so you can start classifying. So I'll show you a table here. So what I'm doing here is that for this weak Jacobi form, I'm labeling what so here there's the index of the form. So that's this column, and then there's the polarity of the form, and then that's that column there. And this is basically the dimension is the number of forms that are slow. Okay. So for instance, if you have index 1 and the polarity is also 1, then the number of forms, well, there's actually only one form, but in the dimensionality is also 1. So that guy is slow. Okay, so it meets this very sparse condition. But there's cases where you get 0, or there's cases that you get less instances. So not every example will lead to a Jacobi form. So in general, the reason why I want to show you this table is just to tell you that if this is our input, then we can categorize basically if it's fast or slow. Okay, so we can tell you which of the two. And you just put this in Mathematica, and our criteria is pretty simple to just go and check. Now, I do want to highlight that the numbers on these columns are pretty low. So that's why they're like needles in a haystack. So the space of Jacobi forms, so if you just decided to fix the index and you say, okay, how many Jacobi forms do I have at index t? It roughly I'm being also hand wavy, but the number of Jacobi forms roughly goes like this t squared. Okay, so you can imagine that at 18, you would have like roughly 18 squared Jacobi forms, but 9 is much, much smaller than 18 squared. So that's why they're not so easy to sort of design. If you just give me randomly a Jacobi form, I will be like, yeah, that was a bad idea. It will not meet your holographic criteria. So in that sense, there are needles. Now, what you might ask, though, is, okay, this is great. This table looks like lots of numbers, very sort of concrete, but what is the physics behind this classification? So can we explore a bit more what's going on in terms of this classifications? So I want to basically highlight now a bit what these criteria are, so digest them a little bit. I'm not spelling out exactly what the criteria in the Jacobi form are, but there are basically two restrictions that make very sort of intuitive then how I'm going to split this discussion. So there's a restriction on the fact that B has to divide T, and this is so that we can give this an interpretation as a superconformal theory with 2,2 supersymmetries. But the most important thing is that as we're trying to impose this very sparse condition on the spectrum, this is a condition on the seed. So let me, so this is a restriction on the central charge of the seed. So I just have a C here, and then again, remember, this is M times. So the seed itself, if you want to have a sparse growth in the elliptic genera, at a minimum, the central charge has to be less than 6. If the central charge of the seed is bigger than 6, you're always going to get hybrid, and that we can prove. This is not, it doesn't guarantee you that you'll be safe, but at least it tells you you will have something to look for. So it's a necessary condition, but it's definitely not sufficient. Okay. Now, as we will see in a bit, this condition, so we can prove it very clearly from the point of view of having this slow growth. But you can also, from the point of view of the symmetric product theory, if you just then look at the spectrum and try to find this marginal operators, which in our case will be also BPS operators, so that they're protected as well. This is also a condition on the existence of a marginal operator in the symmetric product theory. So if the central charge, it's kind of cute that these two things basically give you the same condition, that C had to be less than 6 for the seed. But yeah, there you go. So if you want, one implies, it looks like, well, actually, we know that this one will kind of imply that one. But it's kind of rewarding that we got something that was compatible. So, okay, so from that point of view, if I wanted to, and I'll be finished, I have 2 minutes left.
Alejandra, hi, I think Daniel has a question. It's on the chat. His mic doesn't seem to be working.
Sorry. Okay, I was not paying attention at all at the chat. Yeah. So, yeah. So the thing is that gamma equal to 1/2 it's basically compatible with the condition that I said that gamma was less than 1. But when I wrote down that gamma was d minus 1 divided by d, that's the most that a supergravity theory will tolerate. And so you could have less. And the reason why you could even have less, so I still can interpret this as d, as the number of dimensions, because it will look like d is basically 2, which I would say it's kind of weird. But the thing is that it's because I'm looking at an index. So this BPS states, as you count them from the point of view of the index, they could be lower than this argument of like d minus 1 over d. And that's what happens for d1, d5. And even if you just look at, for instance, even in the d1, d5, there's also a counting of BPS operators without the minus 1 to the f. So it's like an unsigned counting. And that So in D1, D5, you would have expected 5/6. And if you just look at the BPS operators without the -1 to the F, in the strongly coupled point in the supergravity regime, I think you get 4/5, which is still not as much as the whole, like if you don't impose supersymmetry, how many states you're allowed to have. So basically this D -1/D is my upper like patience, like in a sense. And because if I take D to infinity, then it tells me that, yeah, gamma kind of like reaches 1, but it's never quite 1. So that's, yeah. But unfortunately, the gamma equal to 1/2 does not tell me what the value of D is. So, and in the D1, D5, it also wouldn't, that computation wouldn't have told you that you had ADS3 times S3. It's the geometrization of the R symmetry that tells you that you have an S3. So, but okay. But this is a good question. You're welcome, Danny. It's so weird to talk to you through the chat. Okay, very good. So we had this condition that C was less than 6. And so then you can say, well, that's good because actually if you impose like, sorry, so here, if you impose like a bound like this, then you're kind of happy because you know that in super conformal field theories, we tend to be better at characterizing things that have low values of central charge. So if the seed is kind of bounded in this way, this actually gives us much more control because then you can say, well, I actually have a complete classification of n equal to super conformal field theories if C is less than 3. And that's compatible with what I was saying, that C had to be less than 6. And so then you basically can be like, okay, so what happens to these theories? What if I use a supersymmetric minimal model as your seed? Okay, so let's consider, so we'll consider, so this will be a candidate for the seed. And the answer is that it works beautifully. So any n equal to minimal model that you want is basically one of the items that we had in this table. And so here I just put some examples. Some of them are, I wrote a bunch of examples. Some of them are the minimal models. Some of them are examples that we're already familiar with. But just to illustrate that we're identifying basically, before I was kind of showing to you this part of the table, and now I can put in more physics into it. So for instance, the first example, so when I had 1, 1, the central charge was 6. This is basically the K3 sigma model. Okay, so this is D1, D5. This is the example that we love. This is the example that from which then you build the Igusa-Cusp form. That's great. There's also another example that has C equals 6 in this list. In this example, well, you can interpret it as like unwrapping further K3, but it has a more non-trivial interpretation as a quotient on T4 that breaks the 4,4 supersymmetries to 2,2. And this was discussed in a paper. So there's also a string realization here. So it's discussed by Data, Ebenhardt, and Gabriel back in 2017. They have a paper discussing that example. So these are two cases where I know what the roll sheet theory is. I have some understanding of what the supergravity theory is. So these are two examples that were kind of like, okay, we sort of have some understanding from a string theory perspective of what this means. But then there's some other examples that at least I was a bit surprised about. And there's these examples that will have lower values of central charge. So like C equal to 2, 3/2, C equal to 1. And then these are basically the minimal models. So here I'm using the ADE classification to label them. Oof, I'm over time. Okay. And then just to also highlight, there's also, you can also do, there's some examples that have tensor products of minimal models for which you can increase. You don't have to limit yourself to C equal to 3, so you can go a bit higher, and they also work. And there's also some Kasama-Suzuki theories that also work. But this, because these guys go with C bigger or equal to 3, then they don't quite, we can't prove that all of these type of constructions work. We actually have counter examples. There's some tensor products of minimal models that do not show this very sparse condition. Now, the other thing that, last thing, and I'll stop like in a minute. Yeah, I don't have time to discuss this, unfortunately, but the other thing that I don't want you to forget about was that we also wanted these marginal operators. And so now if I have, at least for many of these weak Jacobi forms, a CFT interpretation as a minimal model, I can basically ask, okay, do these minimal models have marginal operators? Okay, so basically things that have H and H bar equal to 1,1. Okay, so you're basically looking for chiral primaries that have charge equal to 1/2, and then if you act with this guy, you get your marginal operator. And the answer is yes. So here's a table where, yeah, I'm just showing to you. So this is the part of the table that you will care about. So here's basically the A, D, E minimal model list. And these are the marginal operators. So single trace in the twisted sector operators that will tell me, yes, I have this little cloud and you can move through this cloud. I wanted to though comment, so just 2 very quick comments here. One, so for, so if the central charge is between 1 and 3, then I just want to make 2 very quick remarks. One is that the fact that the elliptic genus is slow, so we have a complete classification in this case, and we can show that these 2 things are basically tied together. So every time we have, well, they're all slow growing and they all have a marginal BPS operator. What's also interesting is that there's marginal operators that are multi-trace, and there's also marginal operators that are single trace. And those have a different effect from a holographic perspective. So it's also kind of nice that there's single trace and multi-trace deformations. To lifting the spectrum, you need the single trace, but then the multi-trace ones affect couplings. And then what we have explored when you're between 3 and 6 is that we do have counterexamples where having this marginal operator actually does not imply slow. So you can build examples of these CFTs that are not slow growing, they're fast growing, but they do have a moduli space. And I think this is a nice sort of example to try to understand this question about sufficient versus necessary conditions. But okay, I ran out of time, so let me just summarize what happened to you. So this is basically what happened to you. I drew a bunch of circles. And I was talking about the intersection of these 2 circles. Okay, and what I hope that I argued to you is that we have a lot of control now on what is the overlap of those 2 things. Okay, so we have from the point of the view of the weak Jacobi forms, we can identify clearly which weak Jacobi forms meet the criteria. And for certain ranges of the central charge of the seed, the classification is absolutely complete. So we can just tell you unambiguously, these are all the theories built out of a symmetric product, which will meet these necessary conditions. And so then, of course, there's tons of things to do because there's many things that I have not mentioned, but I'll stop here. So because I've talked too much. So thank you for your attention.
Let's thank Alexandra again. Questions, comments?
Daniel is clapping.
I have another question. So this theorem that you mentioned, that if you have a symmetric product with positive coefficients, you only have Hagedorn growth.
Yeah.
So you said that assumes positive coefficients. Now, if you have negative coefficients, true, but is there any, can one do some approximation? If you have only a few negative coefficients, is that good enough, or even the presence of one negative coefficient is bad?
To eliminate the Hagedorn growth?
No, well, either way. Is it, what I'm asking is, suppose you have something with only one negative
well,
coefficient.
I see. Yeah, I should have written down because the criterion for us is actually not what was actually important in order to meet the slow growth. It was not the nature. So I'll write it. Doesn't matter. So as we had like the candidate seed here, our criterion was actually, so you might have thought like, oh, it was important what these coefficients like that are multiplying the seed in the weak Jacobi form are, how many of them are positive or negative. But the way that we basically showed that you could like, well, we showed that generically, like, okay, if the coefficients are positive, then you will get again Hagedorn. But the only possibility for having cancellations was actually dictated by the powers appearing in the YQ expansion. So the polar states, and that's why we got that this bound. So let me flash it. So this was basically, this is a minimal requirement on how the maximal polarity of the Jacobi form is related to its index. And so what was more important was basically which powers were appearing in the weak Jacobi form. Because then what we did, the way that we were extracting the asymptotics, which is basically having some control on, so basically we needed to have some control on how these guys behaved. And based on the powers that were appearing, it's when we could show that this thing collapsed to Kronecker deltas, which are basically just using like a Witten index, like repeatedly, to sort of argue that things were canceling from the point of view of the top exponents here. But that was controlled by the allowed values of N and L in the weak Jacobi form, by those powers, but not by the degeneracies that were multiplying those powers. Well, assuming that the degeneracy was like non-zero for that coefficient.
Okay, I think Daniel has a question on the chat.
Yeah, so because I'm doing everything supersymmetric, exactly, pure Einstein gravity is not in my intersection. I think it's unlikely, but it's a good question, and this is part of my to-do list that I'm trying to convince one of my students to do this. But okay, you can't force students to do this stuff. But what I haven't done super carefully, so we built this generating functional for the perturbative states. I could have been more specific about what the supergravity spectrum is and tell you like, okay, if you have this ADE model, it means that you will have a gravity theory with at least like X number of scalars, X number of gauge fields and stuff. And then I could like ask you a question like, oh, how do I need to do, is there any range of parameters in the ADE classification for which it happens that the number of scalars is 0? I think the answer will be no, but I don't have a proof. This is just my gut, like talking to me. But I think this is part of like something that needs to be done, that we have to digest more what these generating functionals are in a more gravitational language, so we can say a bit more about what these theories are. So because I kind of like, at some point we phrased everything in terms of the CFT, but I'm not digesting things in a way that it's easier to relate it to gravity. So there's other ways that we also are we're also trying to understand a bit what the string compactification will be, but it's yeah, it's a good question. But I'm a believer that pure anything doesn't exist. That's my bias. I'm very biased in that way.
Okay, so we should go on to the next talk because we're running out of time.
Yeah.
Okay,
Sorry.
thanks a lot, Alejandra.
Thank you.
Thanks.
Okay, so let's go on to Kevin's talk. Kevin, can you try screen share? Hi, Kevin.
Yeah. Okay, so how do I do the? Okay.
Kevin, could you speak up? Could you just try
Can you
speaking?
hear me?
Yeah, now I can hear. Yeah.
Yeah. Good. Sorry, just start to share my screen.
Okay, it's perfect.
Good.
Yeah.
Can you see my screen and my pointer?
Yes, yes, yes. That's right. Okay, that's wonderful. Right, you're good to go. Okay, so let's go for the second speaker of the opening session. And I see that Kevin has displayed his usual panache for catchy titles. Applied CFT, he will be talking to us on, so Kevin Goldstein from University of Witwatersrand is talking to us on Applied CFT fire phenomenology. All yours.
Okay, thanks. Well, firstly, thanks to the organizers for inviting me. And also thank you for letting me give a talk, which is actually, I'm embarrassed to say, not on black holes. So fire in the title does not refer to the firewall, although Polchinski will be mentioned. So since one of my collaborators is going to be talking about some of my other work, I thought I would just give a slightly more relaxed talk about some interesting applications we've been looking at recently. Okay, so my collaborators with this work are Sarah Archibald, who's actually a biologist at WITS, Vishnu Jajala, who most of you know, and Vishnu's former student, Luca Pontigia. Okay, so yeah, in this talk, I am literally talking about fire. So you can see here is satellite imagery of fire occurrences in Botswana in 2011. So a black dot corresponds to whether a fire happened in that pixel or not in the year 2011, and a white dot corresponds to no fire. And on the right-hand side is something people should be familiar with. That's the icing model when we're close to criticality. And then that, as we know, is described by some conformal field theory. So biologists have noticed that fire size, if you look at the distribution of the sizes of fires, this follows some power law, which in turn suggests scale invariance. And after having gone to a talk by Sarah, was actually Vishnu thought, well, maybe we could use some tools from CFT to study the phenomenology of fire and these burn patterns, and maybe we could give some new tools to the biologists. So the obvious thing to look at from the perspective of anybody who's looked at CFT is to look at these patterns, these burn patterns, and study correlation functions. And do those correlation functions teach us anything new? Do they actually show, is there actually some sort of scale invariance here? And in more general, is in this 2D pattern, burn pattern, is there some sort of conformal invariance? Good. So just a quick motivation of why one might be interested in this. So understanding fire propagation plays a very important role for biologists in their global climate modeling. So as the climate change, so does the probability of fire, and understanding that interplay is important for climate modeling. And the factors that go into these, how fires propagate and the size of the fires are involved the climate, the fire, and vegetation. In general, as an aside, fire also has an important ecological role. So it destroys habitats, but also releases nutrients into the ecosystem. So the basic tool that we have, the data that we have, is that there's extensive satellite imagery every year all over the Earth. And you can look at a particular area on the Earth and ask whether there is a fire there or whether there was a fire there in a particular time period. So there's a huge amount of data, and there's a scope to study the spatial distribution of fires. Good, so just the basic fire 101. We don't need to know much about fire because I'm just going to be basically talking about the correlation functions that we get. So in a fire, there's 3 basic stages. Firstly, you get ignition, the fire starts, then it spreads, and then it stops. So beyond that sort of basic cartoon of what a fire is, there are many, many models for how fire propagation works, ranging from incredibly complicated models, which try account for a huge amount of variables and how the fire spreads, to kind of very simple percolation models, similar to some of the models people might have been seeing for how viruses spread in societies. So the question that I'm going to be looking at in this talk is the 0th order question is there evidence for scale invariance and conformal invariance? And then the next order question we might ask is, will some basic tools from CFT be useful in analyzing this fire data and assessing various models? Okay. So the starting point is looking at the correlation functions. Right, so we've got a basic field that we can study. So there's the fire field. So the fire field takes on a value 1 if there was a fire at a particular point in the year T, and it's 0 if there was not a fire in that year. Okay. And since we've got certain data, so we're going to take the average, defining this notation. If I take E of X, that's the average of a quantity X over the grid in a year. So for example, if I look at the average of this 1-point function, that basically tells us the density of fire in a particular year over a given region. Good. Right, so things we can study given this fire field, we can look at the 2-point correlation function. So we look at the average over the area of interest of 2 fields at 2 distinct points, and we're going to subtract off the square of the 1-point function, as we often do. Or, oh, that's a typo, that should be a psi. Or we can look at the 3-point function. Once again, we look at multiply 3 fields at 3 different points, take the average over the area of interest and subtract off the 1-point function. Just some notations, I'm going to call the 2-point function of this fire field F and the 3-point function G. There's another field we can define, which we also found useful. So the other one was the 1, 0 fire field. This we call the 1, -1 fire field. And there is it's +1 if there was a fire in a particular year, and -1 if there was not a fire at that particular point in a particular year. And these 2 fields are related by a simple linear transformation. Now, when we look at once again, when we look at the 1, -1 fire field, it's convenient to subtract out the 1-point function. So we look at the 1, -1 fire field and subtract out the average over the whole area of interest to get the field that's useful to look at. Okay. Good. And then what we can study are the 2-point function of this fire field and the 3-point functions of the fire field. And we just define some shorthand. F is shorthand for our 2-point function, and G is shorthand for our 3-point function. Okay, good. So just to compare these two fields we defined, so that the 2-point function of the 1,0 field, so it's only non-zero when both points have fire, when you get 1 times 1. And so that manifestly tells us about fire correlations. And if we look at the 2-point function of the 1 minus 1 field, that's going to tell us about anti-correlation. So if you get fire and no fire, you get 1 times -1, so that gives you -1. Or it tells you about correlations. A fire times a fire gives you 1. And if there are no fire times no fire, -1 times -1 gives you 1. So naively, because there's a simple linear relationship between these the two fields, there should be a simple relationship between the 2-point functions. But because this confused us for a while, actually, we thought there was something wrong with our code. But because we have a finite lattice and non-periodic boundary conditions, that means when in the averaging process, we get actual differences between the 2-point correlation function of the 1,0 field and the 1 minus 1 field. So when we were trying to look at the phenomenology of the fire, we looked at both of these fields to see what kind of information we could extract. Right, so we, taking the 2- and 3-point functions from the data, we fitted them with the kind of thing we would expect if we had a conformal field theory. So we looked at 2-point function, we fitted it to an exponential with some correlation length divided by the distance between the 2 points we're looking at to some power. And then we have something similar for the 3-point function. So here in user notation, x1, 2 is the distance between the point x1 and x2. And x1, 2, 3 is this conformally invariant quantity created out of the distances between the 3 points. Now, as many of you are aware, if we have a conformal field theory, then there should be, well, firstly, these correlation lengths should go to infinity. And also, there's a relationship between these exponents. So a half alpha in our notation should be a third eta. So we, in doing these fittings, we introduced these correlation lengths to take into account both finite size effects and the breaking of conformal symmetry. Good. Please interrupt me if there are any questions. So if in 2 dimensions, there's a theorem by Polchinski that if we have scale invariance, that implies conformal invariance. But what you need for this theorem is you need a Lorentz invariance, which we don't have. You need a quantum theory, which we've got a classical theory, and also you need unitarity. So fires don't unburn themselves. So we expect that if there's any underlying model that describes this system, it should be non-unitarity. So what I find most appealing about this work is being able to say that the non-unitary model is the physical model in this case. So in just to give you the summary of what we found that in the data that we saw, we found evidence for scale invariance, but we found that rotational symmetry is broken. So there's only, in this data, there's only scale invariance, but we showed it in a way that the biologists hadn't thought about looking at. And there isn't this relationship between these exponents that one expects from the usual CFT. Okay. So just to be concrete, what we looked at were grass fires. What the data we were given were grass fires in Botswana and Kazakhstan. And one of the reasons for looking at this is it's a relatively homogeneous vegetation. So if there's any hope for, well, it seems more likely that one might find some sort of scale invariance if your vegetation is relatively homogeneous. And in the data we were given, each each pixel was 50 meters by 50 meters. And the data we given was literally this fire field. So in the data was 1 on a particular pixel if there was fire in that pixel in the particular year, and 0 if there wasn't a fire in that pixel in a year. So here you can, this literally is the areas we were looking at. So this is a piece of Botswana, which was about 1,000 by 1,000 pixels, and a piece of Kazakhstan, also grassland, about 1,000 by 1,000 pixels. Right. So here is an example of the results we found, and we've compared it with the icing model. So remember here we're looking at, say, the 2-point function for fire in Botswana in 2011. And just to remind you, the parameters, A is the amplitude, that's the correlation length, and alpha is our exponent. And okay, maybe I cheat a little, chose a particularly good year, but you see it fits this this exponential pretty well, which suggests that there's a reasonable amount of scale invariance, and the correlation length is quite large compared to the size of the data set. So the data set had a length of about 1,000 by 1,000, and the correlation length is about 1/10 of that. So that's not too bad. If one looks at, so when one fits the icing model, one also often has a correlation length, because if you have some model of when you're trying to model some icing system, it's very difficult to get something which is exactly at criticality. So normally if you have some model of some icing system, you're not exactly at criticality, so you don't exactly have a conformal field theory. So that's why you have some finite correlation there. And I think, at least by eye, both of these look very similar, aside from the fact that we don't have, as we're going to see, we don't have a conformal, we definitely don't have conformal field theory in the case of the phi, because firstly, rotational invariance is broken, and we don't have that nice relationship between the exponents of the second and the 2- and 3-point function. Good. So aside from looking at 2-point and 3-point functions, we wanted to test rotational invariance. So we looked at correlation, we compared correlations along different angles. So for example, I can take if I look at all the correlations along a particular angle, let's say here is, I call that 0 degrees, and I compare it to all the correlations along a different line at 90 degrees to that, if there was rotational invariance, the correlation function should look the same. So the fact that these correlation functions look different tells you that rotational variance is broken. So here is a plot from Botswana in 2004, comparing correlations where we only looked at correlations along 0 degrees, but where our 2 points were at an angle of 0 degrees to each other, and another correlation where the 2 points were where there was a 90-degree angle. And you can see there's a difference in the correlation functions. And we decided to characterize the differences in correlation functions by comparing the area between these two plots. Okay, so here, for example, there's a distinct difference between 0 and 90 degrees, but say, for example, in the same data set, there's very similar correlation between 55 and 145 degrees. Right, so clearly rotational symmetry is broken. Probably this wasn't surprising to the biologists, but it was a bit surprising to us because we thought if you have scale invariance, you should have conformal invariance. But as I've said, we shouldn't have expected that. So, for example, one possible mechanism for this breaking of rotational symmetry is wind, which obviously plays an important role in fire propagation. Good. So here's these are just plots of to demonstrate this failure of rotational in variance. So if you look at the data, look at various angles and the differences between the correlation functions, there's some peak at a particular angle in 2002. Okay, we would like to see if that correlates with the prevailing wind directions, but we haven't yet done that analysis. Good. Right. So then, what we looked at next was looking. Don't worry too much about the data because we couldn't. Well, if you can spot some patterns in it, please let us know. But we couldn't really spot any patterns. We looked at the 2-point and 3-point exponents as how they varied over time, and we were a little bit disappointed. There didn't seem to be any universal exponents in the system, and there definitely wasn't a nice universal relationship between the 2-point exponent and the 3-point exponent. So yeah, we'll have to study that further to understand what was going on. Good. So that was a plot, of looking at how the exponents vary from year to year. And also we looked at other things like how the correlation lengths in our data varied from year to year. Once again, we didn't see any coherent patterns. We also tried to see if there was anything in our fits correlating the weather. Say, for example, we looked at the rain, the temperature. Those are the kind of things one might expect to affect a fire, and we didn't find any convincing correlations between our fits for these correlation functions and the weather data, which was once again a little bit disappointing. Okay, well, I've gone through this a lot quicker than I was expecting. But just in summary, what we did, so we looked at spatial correlations in fire phenomenology. And at least what we've shown is that we managed to convincingly show that there is some scale invariance. So the correlation functions are definitely a useful tool in this arena. And in future, we hope to possibly differentiate various models and extract relationships between exponents, models, and the data. Good. So, and thanks. Sorry, I went through that very quickly. Thanks.
Thanks, Kevin. Okay. Okay, that leaves time for a lot of questions, also for a bigger break. So, any questions or comments?
Yeah, I mean, I guess I thought it'd be nice to bring some of this work to people's attention because we really know very little about 2D non-unitary theories with scale invariance. So I was hoping if anybody knows about these theories or have any ideas, this might be some fun things to play around with. Thanks.
Kevin, I have a question.
Yeah.
Could you apply this to fires in California?
Okay, so this is to grassland fires. So whereas I think I don't know much, but so the fires in California are mainly woodland fires, if I'm not mistaken. But yes, I think it'd be more difficult to apply in California because it's not as homogeneous. But we have been thinking about applying this to woodland fires. But in the case of Botswana and Kazakhstan, you've got large homogeneous grasslands, and which are also relatively flat. Whereas I think in California, the topology is more complicated and it's not as homogeneous. Mm-hmm. But yeah, it would be interesting. We could definitely try.
So I didn't understand. You have these correlation functions. Is there a predictive model there? Is there a prediction there somewhere? Or so are you still doing pattern recognition?
We don't. There's a whole plethora of models that biologists have. We're just suggesting that these techniques could be used to differentiate between various models and be another tool.
Okay.
And studying the various models. But there's a whole lot of models which I haven't talked about that are out there.
Okay, so if there are no other questions, thank you, Kevin, again. All right, so we reconvene at 2 p.m. 2 p.m. Lisbon time. Thank you. Thanks, Kevin.
Sure.
Okay.